Okay. In the last class, we have learned how to find the matrix representation of given linear transformation T with respect to the ordered basis alpha and beta. And in section 8.2, we have learned the concept of similarity and how to find the matrix P that makes P inverse AP is the A prime, which is the matrix representation of linear transformation T. Okay, now in section 8.3, we will learn how to find the orthogonal matrix P that makes the given matrix which is similar, which makes a given matrix to a similar diagonal matrix through the matrix, orthogonal matrix P. So it works for the symmetric matrices. So in section 8.3, we deal with the symmetric matrices mainly, because the symmetric matrix has many interesting properties. So in this section, we learn every symmetric matrix is orthogonally diagonalizable. And then we will be able to use those properties to define a matrix function by using the matrix diagonalization. Here, we start with the orthogonal matrix. If a matrix A, invertible matrix A, satisfies A inverse is equal to A transpose, then we call A is an orthogonal matrix. If A transpose is equal to A inverse, then we call it is an orthogonal matrix. If A is an orthogonal matrix of order n, then the rows of A are also normal vectors. And columns of A is also orthonormal vectors. Okay? It's orthogonal each other, and the length, the norm is 1. Okay. And A is invertible, and the norm of AX is same as norm of X. If A is an orthogonal matrix, it preserves the norms like this. These are all important properties for the orthogonal matrix. With those knowledge, you can check the followings. If A is a given matrix like this, if you can check the A transpose A is an identity matrix, then you can say this given matrix is an orthogonal matrix. So it's very easy to check whether the given matrix is orthogonal matrix or not. Just if you have A, then check A transpose A, whether the A transpose A is an identity matrix or not. Okay? If it's an identity matrix, then it is an orthogonal matrix. Let A and C are symmetric matrices, square matrices of same size. And if there exists an orthogonal matrix P such that C is equal to P transpose AP, then C is called orthogonally similar to A. Not only similar, orthogonally similar. If C is equal to P transpose AP, okay, instead of P inverse. It's much easier if P is an orthogonal matrix to deal with. Orthogonally similar. For a square matrix A, if there exists an orthogonal matrix diagonalizing A, then it is called, A is called orthogonally diagonalizing. If you can find the orthogonal matrix P and a diagonal matrix P such that P transpose AP is equal to C, P transpose AP is equal to D, then we call it orthogonally diagonalizable. And the P is called the matrix the matrix P is called a matrix orthogonally diagonalizing A. P transpose AP is a diagonal matrix. Okay. Now, this theorem 8.3.2 says every eigenvalue of a real symmetric matrix is a real number. Every eigenvalue, real number. The real symmetric matrix has all real eigenvalues. Okay? The proof of this will be given in the theorem 8.7.2. 8.7.2. I will show you it in here. Here I'll find 찾기 8.7.2 here. Here. If A is equal to A transpose, if symmetric, or if is a complex matrix, and if is a complex conjugate is equal to A. So this proof is much clearer and easier. So if you have a real matrix, then A is equal to A transpose, and also is equal to A conjugate transpose is same as A. In that case, all the eigenvalues of A are real numbers. Suppose lambda is an eigenvalue of A. Then there exists a non-zero vector x such that Ax is equal to lambda x. If you multiply x conjugate transpose on both sides, then you will have x conjugate transpose Ax, okay? Which is the same as x conjugate times lambda x here. The lambda is a scalar, so lambda can come out. So you have lambda times inner product of x and x. This can be written as lambda times the norm of x squared, like this. So you have this is this. So lambda can be written as this. Since x is an eigenvector, this is a non-zero. So this is the denominator is not zero. So all you have to show is if we can show x star Ax is a real number, then it says lambda is a real number. So all you have to show is the conjugate of x star Ax is same as x star Ax. This is all you have to show. If we show this, then it's done. Then lambda should be a real number. Okay? Let's see. This can be written as this split. And the conjugate of Ax is, and here, since this, okay. And yeah, this can be written in here, yeah, this conjugate transpose here. So since x star is x conjugate transpose, you have one more conjugate here. So conjugate is gone. So x transpose of this is left. This can be written as this. Since so x is equal to x the A conjugate transpose. So x conjugate transpose and conjugate and transpose turning out to be this. Okay, and it's because of this. And you know, this can be splitted in this way, and this can be written in this way. Here, the x conjugate transpose is x star, A conjugate transpose is A. So this now we have shown this is same as this. So conjugate is same as itself, which means this is real. That this is a real number, so lambda should be a real number. So every eigenvalues of symmetric conjugate symmetric, we call it a Hermitian matrix. If A is equal to A conjugate transpose, then all the eigenvalues of A are real numbers. This is what you have shown. Okay? This is a better proof. So I showed you if it's a real symmetric matrix, then A is the same as A conjugate transpose. So A should, the eigenvalues of A are real numbers. With those in mind, which is very important, and we will learn it over again at section in the theorem in section 8.7. So now we have a symmetric matrix here. Then you can easily check the characteristic polynomial. Then as you see, the eigenvalues are all reals. It was guaranteed because this was a symmetric matrix. So it should have the real eigenvalues. So we already know it. If a square matrix A is symmetric, the eigenvectors of A corresponding to distinct eigenvalues are orthogonal to each other. If eigenvalues are distinct, then we already know corresponding eigenvectors are linearly independent. But not only if it's a symmetric matrix, it is not only linearly independent, but also orthogonal. In order to show the orthogonal, what you have to show is the inner product is 0. Then we call it's orthogonal. So let's say V1, V2 are eigenvectors corresponding to distinct eigenvalues lambda and lambda 2. Okay, then we can write the left-hand side, lambda 1 times V2 transpose V1. Then we show this is same as lambda 2 times V2 times to transpose V1. Then we can subtract this one and this one to make it 0. And then lambda 1 and lambda 2 is not 0. So this inner product should be 0. That's what we are going to do. So let's start from here. This can be written as this, because lambda 1 is a scalar, so it can come in between. And this lambda 1 V1 is a V1. So, but A is a symmetric matrix, so A is same as A transpose. But then this can be written as the transpose of A V2. But A V2 is lambda 2 V2, so this can be written as lambda 2 times this, because lambda 2 is a scalar. The transpose of lambda 2 is itself. Okay? It's a 1-by-1 matrix, so transpose is itself. So this is same as this. So if you subtract this to here, then lambda 1 minus lambda 2 times this is 0. But lambda 1 minus lambda 2 is not 0. So this term, V2 transpose V1, should be 0, which means V inner product of V1 and V2 is 0, which means V1 and V2 is orthogonal. So if you have a distinct eigenvalues, lambda 1, lambda 2, then its corresponding eigenvectors are always orthogonal. Not only linear independent, but orthogonal, which is much better. So, the following theorem is given. A square matrix, for a square matrix A, if A is orthogonally diagonalizable, if and only if A is symmetric. So if A is symmetric, we can show A is orthogonally diagonalizable. And also if A is orthogonally diagonalizable, we can show A is symmetric. Let's start from the left-hand side. Suppose A is orthogonally diagonalizable, then A can be written as what? P transpose, so a P transpose, we have the orthogonal matrix P and diagonal matrix D such that P transpose AP is equal to D, isn't it? Yes, orthogonally diagonalizable. But D is a diagonal matrix, okay? And all the eigenvalues are real, okay? Already. And also, since it's a diagonal matrix and D is equal to D transpose, D is equal to D transpose. So P transpose AP is equal to D, but D is equal to D transpose because it's a diagonal matrix. And so this can be written as the transpose of P transpose AP, which can be written in this way. So we have this is same as this. So we want to show this A and A transpose is same. So we start from here. We multiply P and P transpose on left and right. So we have this. But PP transpose and PP transpose are all identity, isn't it? So this is identity here. So we have A is equal to A transpose left, which means A is a symmetric matrix. So if A is orthogonally diagonalizable, then A is symmetric. And the other direction is also not difficult to show. So I will left it for you as a homework problems. You can read the proof here. Okay, so whenever you have a symmetry matrix, you know the matrix is orthogonally diagonalizable. There exists the orthogonal matrix P and D that makes P transpose AP is equal to D. If you have a symmetry matrix. So symmetry matrix has a very nice property. If A is a symmetric matrix, then A has n eigenvectors forming an orthonormal set. If it's a symmetric, then it is orthogonally diagonalizable like this. P transpose AP is equal to. And this P is what? Orthogonal matrix. So columns of orthogonal matrix are all orthonormal vectors. And if it satisfies this, then AP is equal to PD, which means column vectors of P are eigenvectors. So you have eigenvectors which are also normal vectors. So you have the column vectors of orthogonal matrix P are all eigenvectors of A. So you have also normal set of eigenvectors. That's what it says. Since P transpose AP is equal to D, so these also normal column vectors are all eigenvectors of A corresponding to the eigenvalues in the diagonal entries of diagonal matrix D in the order. Okay. So this is also very nice property. So whenever you have a symmetric matrix, then you have n also normal eigenvectors. So it gives us the following theorem. So if you have a symmetric matrix, it is orthogonally diagonalizable, and it has n also normal eigenvectors. Done. This is this combining the fact that we have explained. Here's the examples. For symmetric matrix A, as you see, this is symmetric 3 by 3 matrix. Then this is orthogonally diagonalizable. So find the orthogonal matrix P, then make P transpose AP is equal to D. So from A, all you have to do is find the characteristic polynomial. From this characteristic polynomial, you have the eigenvalue, 3 distinct eigenvalues, -3, 0, and 6 in increasing order. Note that all the eigenvalues are distinct. So you will have 3 linear independent eigenvectors. Okay? And also, since it's a symmetric matrix, these should be orthogonal already. If you have 3 linear independent and orthogonal vectors, x1 and y1 and x1 and y2 and x3. So you already have y1 and y2 and yg that are orthogonal. We need to have also normal vectors, g1, g2, g3. So you just normalize this to as a g1, g2, g3. Then the P matrix P is the orthogonal matrix whose column vectors are g1, g2, and g3, which are also normal eigenvectors. Okay? Then if you multiply P transpose AP, then you will have a diagonal matrix whose diagonal entries are -3 and 0 and 6 in the order. You can easily check it. Okay, now this is another symmetric matrix. Okay, 3 by 3 symmetric matrix. It has 2 distinct eigenvalues, -3 and 6. But this is a symmetric matrix. So we know it has 3 also normal eigenvectors. It has. Even if it has a algebraic multiplicity 2 here, but we know it has 3 linear independent eigenvectors. Then, and also we can find the 3 also normal eigenvectors. So from here, from lambda 1 is equal to -3 with the algebraic multiplicity 2, we have 2 linear independent eigenvectors like this. From eigenvalue lambda is equal to 6, we can find, from 6, we can find another eigenvector x3. And they are orthogonal each other already. So we now have a 3 linear independent eigenvectors, x1 and x2 and x3. Okay? And we know x3 is orthogonal to x1 and x2. But here x1 and x2 are only linear independent, but not yet orthogonal. So we use a Gram-Schmidt orthogonalization process on x1 and x2 to find y1 and y2. Then, and y1 and y2 are orthogonal vectors. So you normalize this y1 and y2 to find also normal vectors g1 and g2, and just you normalize the x3 to g3. Then you have g1 and g2 and g3. They are all also normal. So you form a matrix P whose column vectors are g1 and g2 and g3, which are all also normal eigenvectors. Then you will have P inverse AP, P transpose AP is equal to a diagonal matrix 3, 3, and 6, -3, -3, and 6. Okay. That's it. That's the end of section 8.3. Any questions? Yes. If you learn the orthogonal diagonal, if you can find the orthogonal matrix that orthogonally diagonalizing the given matrix A, then you can define a matrix function. And like this, you have learned this Taylor expansions from the calculus class. You had only one variable like this. But this can be extended to a matrix function like this, log of I plus identity matrix plus A matrix, in a similar way like this. Here you have a radius of convergence. Here you do have a similar condition. Here it depends on the eigenvalues of A. If you like this, then how you define this A square n cube n fourth? This can be defined with this. By the similarity, you can find the similar matrix J, which is a direct sum of this block matrix, block diagonal matrix like this, block diagonal matrix, whose terms like this. This is a typical form of Jordan canonical form that you will learn in chapter 10. If you can do this, which you have learned this in the calculus class, now you have learned this. And you will learn particularly on this form in chapter 10. Then, from here, you can define a matrix function on this Jordan block. If each term of this converges like what you have here, then you have the existence of this matrix function is guaranteed. If this is guaranteed, then the power of this are defined. If the matrix power of this is defined, then the matrix power of A is defined. If matrix power of this is defined, then this polynomial, matrix polynomial is defined. So you now have a matrix function f of A from here. That's why you are learning matrix diagonalization and Jordan canonical form. And that's the reason that you have learned the calculus and Taylor series, Maclaurin theories. And these are all together to define a matrix functions. Okay. Okay, and that's the end of section 8.3, and we will start quadratic form. Any questions?